Hello guys, welcome. In this video we will see next type of problem, the most widely used application problem known as the truss. So in previous videos we have discussed about the various applications and different boundary conditions where we apply the analysis procedure specific to the boundary conditions in the physical structure. In this video, we will see another new truss member where point of view change. So, what is a truss? So, truss is a structured element that is designed to support only axial forces. So therefore, it deforms only in its axial direction, and it has a basic condition where the cross section of a bar can have an arbitrary geometry, but the dimension of the cross section of the bar must be always smaller than the bar. So such members will be called as truss. So truss, it is usually made of several bars devoted or welded together. So we have various applications. I will point out some few examples of truss bridges, barrows. So these are some applications of trusses, and it will be constrained to only the axial loading condition. So this is a simple structure of a truss. So as you see, we have now in previous topic, we have derived the stiffness matrix. So as still what we have previously used, whatever the final element equation remains the constant, but the stiffness matrix formula will be a different one for truss. In this, the element itself will be a truss element, so that we have this formula, and it is in symmetric matrix as you see from this matrix. And one more thing, in truss there will be displacement. There will be two displacement in x and y. So as for previous problems where we had only one displacement at the node, whereas from trusses we have displacement both in x and y. That's what we can see at all the nodal point. We take this as node 1. Node 1 we have u1, u2, which is displacement in x, displacement in y. When you go for another node 2, you have displacement in x and displacement in y, similar to the, for example, we have 1, 2, 3, 4, 5 nodes. Obviously we have 10 displacement values. So this is what the stiffness matrix which we have to remember while you are solving your truss problem. So final element equation remains constant for all the FE problems. Only changes will be in the stiffness matrix formula. So this is the formula which we have derived, from the derivation of stiffness matrix for truss. This is your end result which you have to remember while going to more problems. Now we will solve simple problems so that will be much familiar, so that we can go for actually larger complex problems. So we take a simple truss element. For this particular truss, you have to determine the displacement and stress in element 1 and 3. This is the element 1 and 3. So for this element, you have to calculate the displacement and stress. So they have given the Young's modulus, which is 70 gigapascal. Convert that into Newton per mm square. Area they have given. Load at the node 1. So at node 1, this is node 1. We have an axial load of 4 kilo. I have converted that into. Now, before starting the truss, you have to calculate or formulate the coordinates of all the nodes. So in this problem, we have 3 nodes, right? Node 1, node 2 and node 3. Take any one node as an origin. As for this problem is considered, I am taking node 1 as origin. So this is 0, 0. This is 0, 0. The distance, this is y-axis, this is x-axis. So right side of this origin will be positive x. Left side of this origin will be negative x. Above this origin will be positive y, and below it will be negative y. So now you formulate. So this distance from here node 2, this is along the origin. So your y-axis will be 0. It is 500. So it is a negative side of the origin. So minus x. So we will have minus 500, 0. That is the coordinate value of node 2. Similarly, when you go for coordinate value of node 3, it is below. So obviously your y-axis will be minus, and it is of positive side. When you draw a line from here, so this length will be 400. So it will be 400 minus this y distance. It is minus 850. So this is the coordinate value which you have to evaluate. Once you know the coordinate value, you can straight away go calculate the equivalent length of element 1 and 2. What is the equivalent length of element 1 and 2? So this is element 1, this is element 2. What is equivalent length? You know this is the line, you know the coordinate value of start of the line and end of the line. And how will you calculate the length of this line? That is what we are calling here as the length of the element. So root of x2 minus x1 the whole square plus y2 minus y1 the whole square. We have all the coordinates values, substitute, you get equivalent. LE1 means equivalent length of element 1. And next, direction cosine L1 M1. So as we have seen in our previous section, the substitute, you know, x minus x2 x1 LE1, calculated from the previous substitute, we get the L1. Similarly M. So this is L cosine, this is M cosine. Now you repeat the same step for the element number 2. Element number 2 is root of x2. When you go for element number 2, here you have node 1 and node 3. With this element, the related nodes here are node number 1 and node number 3. So as you go to, so you can calculate the equivalent length of element number. So once you are done with element number 2, equivalent length of, you can straight away go and calculate the direction cosine L2, and that's it. After this, the substitution. So for element number 1, so you know area it is common, Young's modulus is common, equivalent length we have calculated, substitute respective L1 M1 formula, which you will calculate if you substitute and simplify. This will be your final stiffness matrix. Similarly, do it for the element number 2, A2, area it is common, Young's modulus is common, equal to length alone vary. Similarly, we have calculated the L and M cosine. For the element number 2, you substitute and simplify. This is your stiffness matrix 2. So now what is the next step? Next step, you have to assemble the K matrix, both the K1 and K2. If you assemble, you will get this. So we have 6 rows, 6 columns. How it is? Because here we have 3 nodes. So at each node you have 2 displacement. So for 3 nodes you have 6 displacement. So hence your final assembled global stiffness matrix will be a 6 cross 6 matrix. That is what you have got here. So after assembly K1 and K2, this is your final stiffness matrix. So now you apply the stiffness matrix in finite element equation. That's it. So now you have to go for the boundary condition. So boundary condition is very important in truss problem. Now you go for boundary condition is nothing but you have to calculate the values of displacement and force from the given problem. You have to go to the physical structure of the given problem, evaluate the displacement and force values depending upon the given condition, and just substitute. That is will be boundary condition. If we go for here, if we go for the given problem, we can see node 2 and node 3 is fixed. So what does it mean? So there will not be any displacement in node 2 and node 3. There will be displacement only at node 1. So node 1 related to u1, u2. u1, u2 will be unknown here. If you go for node 2, u3, u4 it is completely fixed. So u3 and u4 will be 0. When you go for node 3, the displacement is u5 and u6. It is completely fixed. So hence u5 and u6 will be 0. And what about the force? So similarly in node 1, F1, F2. F1 is the force which is on the direction of X. F2 is the force which is acting on the direction of Y. So F1 is 0. There is no force. F2 there is a force acting in the negative Y direction. So it has minus 12 into 10 power 3 Newton. What about node 2? Node 2, no. F3 it is 0. F4 it is 0. Come to node number 3. Node number 3, your F5 is 0, F6 is 0. That is what the boundary condition here. Only F2 it is minus 12 kilonewton, whereas other force it is 0. Node 2, node 3 is fixed, so U3, U4, U5, U6 is 0. You just apply all these values in this, applying the boundary condition. You apply here, so U3, U4, U5, U6 will be 0. F1, F3, F4, F5, F6 will be 0. So neglecting the respective rows and columns of this multiplying matrix, you will get only U2 and this is U1 and U2. So as usual, you expand this equation, you have two equations and two unknown. So simplify it straight away using your calculator. You can calculate U1 and U2, which is the displacement of node 1 in X and Y direction. In X direction, U1. So U1 is the displacement of node 1 in X direction, minus 0.57 mm. What about U2 then? U2 is the displacement of node in Y direction. So that's it. Once you are done with the displacement, you can straight away go for the stresses. As we see in the start of the problem, they have asked to calculate the displacement and stresses. Straight away go for this formula. You know all the values are known. Young's modulus, equivalent length, L cosine, M cosine of element 1, U1, U2, U3, U4. Element 1, it is related to the element node 1 and node 2. So hence you have U1, U2, U3, U4. All the values are known. Substitute and multiply. This is F4. This is 1 cross 4. This is 4 cross 1. If you multiply, you will have a 1 cross 1 element. That is only a single element. That is minus 79.94 Newton per mm square. The same thing you have to repeat for the element number 2. So a change will be there in equivalent length. Element number 2 and cosine of the element number 2. And similarly, element number 2 it is related to node 1 and node 3. Therefore, hence you will have U1, U2 which is related to node 1, U5 and U6 which is related to node 3. As usual, substitute everything and multiply these two. It is an 1 cross 4 and this is 4 cross 1. Obviously, if you multiply, you will get your final 1 cross 1 element which is this minus 100 per. If you have minus, then it is a compressive stress. If you have plus, you can write it. It's not necessary, but just you know, when we have a stress negative value, call it as a compressive stress. That's it, guys. Thanks for watching. Please leave your comments if any in the comment section so that can improve in the coming videos. Thank you, guys. Take care. Stay safe. Stay healthy.